Okay. All right, so so last Tuesday we consider two jointly absolutely continuous random variables, and and we have recalled conditional PDF of random variable x, given that random variable y is equal to a specific value little y. All right, so now we define the conditional expectation of x given that random variable y is equal to little y. So it's defined as so that is so we use the conditional PDF of random variable x given that random variable y is equal to a specific value little y. Okay. So this is the definition, and we can so that this integral can be divided into two formula. The first formula x here is the ratio if the marginal PDF of random variable y at little y is positive, then this integral is actually this formula. So the numerator is the integral of x times with the joint PDF of f(x), x and y. Okay, and but here little y is fixed. Okay, so when little y is fixed, the integrand is a function of x, and we integrate over all x in R. Okay, and the other is actually okay. So when this value is equal to 0, all right, then because the conditional PDF of random variable x given random variable y equal to the specific value little y, and is equal to the unconditional PDF of random variable x. Okay. Okay, and that we know this is actually expectation of x, and so provided that the integral exists all right, so we have that, and if x and y are independent, then we know that the conditional PDF of random variable x given random variable y equal little y, and is equal to the unconditional for all x, y in R. This is from proposition 6.5.d. Right? So, and then the conditional expectation of random variable x given that random variable y equal to little y becomes to be which is just the expectation of x Oh, okay. So let me see. Oh, I forgot to put it for, okay. For almost, oh, I'm sorry. For almost all, square. All right, so this is for almost all. Yeah, so only for almost all, I'm sorry. Okay, so for almost all point xy in R square by proposition 6.5.d. So that this is true for almost all y in R. Okay, provided that E of x exists okay, so if they are independent, then for almost all y in R, this conditional expectation, right, is equal to the unconditional expectation of x. Okay. So if the conditional expectation of random variable x given that y equal to little y exists and it's finite, okay, for almost all y in R, which means that for all y in a Borel subset, we say delta of R such that with the length of R minus delta to be 0. Okay. So this is the meaning of for almost all. Okay. Then we can define. So we can define a real value function on R as follows. Define gy to be right. So if y is in the delta, the Borel's set delta, then the value is equal to this conditional expectation. And we also denote this is 0 if y is not in delta. Okay? Of course, you can assign the value arbitrarily, but 0 is a good choice for that. Okay. And you may define to be 1 or 2, anything. Okay. Just now if G is Borel measurable, okay, then G of y is a random variable, and it's called a version of the conditional expectation of x given random value of y. So denoted as expectation of x given y. Okay? And the name, the reason for the name is because it contains this information. And it's called a version because that when we establish the function g, okay, for all the y which is not in delta, this value is arbitrarily assigned here. So you have different other choices to establish a function g. Okay, so it's called a version of that. All right, and for an outcome omega in the sample space, then we have this random variable has value at omega, which is, so by definition, okay, because that a version of this random variable, the conditional expectation of random variable x given random variable y, is the data processing of the random variable y by g. Okay, and so this is g of y omega. Okay, and so that is expectation of x, y equal to y omega, and the other is 0. If y omega is in delta, if y omega is not in delta. Now, the expectation, so now by proposition 5.2.1, the expectation of this random variable is the expectation of g of y, okay, and right, so proposition 5.2.1 give us the formula, so it's g of y, f, right, because random variable y is absolutely continuous with this probability density function. Okay, so this is one, and so this. Okay, and because the length of delta complement, okay, so this is called the delta complement, all right. The length of delta complement is 0, okay, right. So sometimes we can say okay, so yeah, this is the exact this, but in the notation that we usually write it down like okay, even though as a function of y, this function defined for almost all y in R, but we usually denote that even though this is integration x in delta, but we will use the notation as the same integral, okay, the same integral, okay, since even though that is defined for almost all y in R, i.e. for y in delta. Okay. Okay. So this is actually the actual integration, but if the integrand defined for almost all y in R, then we can replace this as this one. Okay, actually they have the same. This express the same integral. Okay. So you may write this integral as here over delta or over the whole R. Okay. All right, and of course, provided that the integral exists, or provided the integral, we need that the integral converges absolutely, okay, as needed in proposition 5.2.1. Okay, now we state our proposition 7.5.1 for an absolute continuous. Okay, so let x and y be two jointly absolutely continuous random variables with a PDF of xy. Okay, if x has a finite expectation, then the conditional expectation of random variable x given that random variable y is equal to specific value d2 y. Okay, this is, exists and it's finite. Okay, for almost all x, y in R, i.e. for all y in a Borel subset delta of R such with the length of delta complement, which is R minus delta, to be 0. Okay. All right. So the first we know, then this quantity exists and is finite for almost all y in R, and the function g of y as defined in 7.5.1. So we call this is 7.5.1. It's Borel measurable on R, so that G of Y is a random variable, okay? And the expectation of, so that the expectation of this random variable is equal to E of X. Okay. So which means that this random variable has a finite expectation, and they are equal. So maybe I will say, and this one has a finite expectation. With expectation equal to E of X. Okay. So X has a finite expectation, give us a lot of things. The first thing is that here, that this conditional expectation of random variable X given that random variable Y equal to specific little y, so this value exists and is finite for almost all Y. Okay. All right. So it says for the condition here. The second thing is that the function G of Y is Borel measurable. Okay. So when we define here, okay. So you see that G of Y and this G of Y is Borel measurable. So we require, okay, we have requirement. So we know G of Y is Borel measurable on R. Okay. All right. So we have this, and the third thing is that this random variable has a finite expectation. Okay. And its expectation is equal to the expectation of X. Okay, so this is the so this condition is sufficient to guarantee 1, 2, 3. Okay, and the important thing is here is this identity. Is this identity. And there's no requirement for Y, you can see here. The only requirement is that the random variable X has a finite expectation. Okay? And the requirement for Y is that X and Y are jointly absolute continuous. Okay? So you can select arbitrary Y, okay? So that X and Y has a joint probability density function. Okay. Then that you can use Y as a sign information, and then you compute conditional expectation of X given Y. Okay. And we know this is actually a function of Y. So you need to find the G function, and the G function, okay, contain this one. And the computation of this is based on the conditional probability density function of random variables x given that random variable y equal to little y. Okay. Right. So once you compute this, all this one, and then you establish the function g, and then of g of y give you a version of the conditional expectation of random variable x given random variable y here. Okay, and then you compute the expectation here according to this formula. Okay, and this expectation is exactly the unconditional expectation of x. So once again, this is an indirect way to find the expectation of x. If the direct computation of this expectation is difficult. Okay? In many situations, the direct computation of this expectation is actually difficult. Okay, so you can use this indirected way, okay, to find them. So, any questions about the statement? Any questions about that? Okay, so the idea is quite similar to the discrete case. Okay, but so we will apply. So we'll use a result called Probability theorem. Okay, in analysis there. But so note that x has a finite expectation. If and only if that the expectation of the x value of x finite. Okay. And also know that the joint PDF of x and y is equal to the marginal PDF of random variable y times the conditional PDF of random variable x given random variable y equal to specific variable y. And this is for almost all the points xy in R square. This is by proposition 6.5.a. Okay, so we know that. Okay, so this identity holds for almost all points in R square. Okay. Now, since, so we check that. Okay. Okay, so that here, this product is the f of xy. Okay. So if so, f of xy is the integrable functions. Okay, and it has two variables x and y. So we take the absolute value and integrate over y. Okay, integrate over y. Right, so we do the integration. Now we have this one. Now this product is equal to the joint PDF for almost all points so that that they would have the same integral here, and this is actually the marginal density function of random. Oh, sorry. This is equal to the marginal density function of random variable x. And so this is finite. Right? And this is finite for almost all x in R. Okay? So we know that this is true for almost all x in R. Because the identity is for almost all points in R square. Okay? So this is true. And we evaluate now because this integral over y, okay, converges. So you can see that this integral is finite for almost all x. And so when we integrate over the R, okay, of right? So again, this is our f. Don't use f because you may confuse with the CDF. So I use G. All right, it's G. Okay, and so this is equal to from here we know this is okay. This integral. Right, because the inner integral equal to this product, but this is exactly the expectation of the absolute value of x, and we know this is finite. Why? Because x has a finite expectation. Okay, so we have this one. Right, with that. Okay. So by Fubini's theorem, we have first of all the double integral of the integrand okay. So the double integral here, its integrand is our g function. Okay. So the double integral converges absolutely. Okay. Which means that if we take the absolute value of the integrand, then the double integral is finite. Okay, which means that we say that this integral converges absolutely, which means that the double integral of the okay, is finite. All right, this is the meaning. This is the first assertion. The second assertion is that the two integrals per Cx defined to be y in R, x and by phi y okay, so these two integral converges absolutely for almost all x in R and for almost all y in R respectively. Okay. All right, and this integral converges absolutely for almost all x in R has been, it's just here. Okay, I just restate that, okay? Because this, okay, so this computation justify that, so this is old, okay? But this is new. This is new. Okay? So you can say that this is due to, this is here. Okay. Right? So this is all, this is given actually. But this is new. Okay. And also, this is new, okay? So that by phi x and per c x and by phi y are Borel measurable. Okay, so they are Borel measurable. Okay. And the two integral per cx dx, the two integral by phi y, okay, the two integral converge absolutely. Okay. Even though per c x is defined for almost all x in R, and by phi y also defined for almost all y. Okay, but then these two functions are also Borel measurable, and if we do the integration, then these two integral converges absolutely. Okay, and the third one, the double integral of x fy of y All right, the double integral is equal to equal to this integral and also equal to dy. All right, and what is that? This is the iterative integral. Okay, and this is the okay. So basically, you can exchange the order of integration. Okay, and this is also given. Okay, so this go to here. All right, but this is new. Okay. Okay, and also the identity, they are all new. Okay, this is new. Okay, this is new. Right. So by checking these two integral, okay, to be finite. This one is finite for almost all x in R, okay, and this is finite. Okay, now with these conditions, and then so we can apply probability theorem to give 1 to 3. We have these 3 consequences. Okay, and we use these 3 consequences to prove, to finish the proof of this proposition. All right, so now, since the expectation of x given y equal to little y, x here, okay, so this one exists, right? Why? So we look at this one corresponding to which one? Here, right? So that this is f of okay. And we know this integral, all right, converge absolutely, right? With for almost all y in R. Okay, so for almost all y, that this integral converges absolutely. Okay, so things and which converges absolutely by 2 in above Okay, so that this integral converges absolutely, which means that this integral exists and is finite for almost all. Oh, I forgot. For almost all y in R by 2 in above. Okay. All right. So that this integral, this value exists, is finite for almost all y in R. Okay. Okay. So this is the first assertion that this quantity exists, is finite for almost all R in R. All right, and also by 2 in above, by 2 in above, that and G of y is Fourier measurable. Oh, I forgot. I forgot to say here. For Cx and the phi y are Fourier measurable for almost all x in R and for almost all y in R. All right, and the two integral. Okay, so they are Fourier measurable for almost all x in R and for almost y in R. Okay, I forgot to write down. Sorry. So that G is Fourier measurable on R since phi y, which is f of and okay, so you can see that this is actually okay. It's Fourier measurable for almost all y in R. Okay, so this is also so the second assertion is also from 2, the item 2 there. All right, by 2 in above. Okay. And finally, expectation of and So the expectation is here. Oh, I have to correct it. It's y, not x. Sorry. Here, this is because we integrate over y. Okay. So this is the y in R. Okay, it's this one. All right, and so all right, and this integral okay, so this integral is here. Okay. Okay. This iterative integral is equal to this integral. And so this is equal to this one. So we can exchange the order of integration. Okay. So this is by 3 in above. And here, because so this integral dx dy here, okay, because that this product is equal to the joint PDF for almost all x, y in R. Okay, so that I have this and so this is expectation of x. Okay, and we have done. Okay, so we have this version. Right, so let's take a break up to 2:35. All right. So we have considered conditional expectation of a random variable given another random variable in two cases. The first case is that both two random variables are discrete. And the second case is that these two random variables are joined to the absolute continuous. Okay, and in chapter 6, we actually discuss conditional distributions for mixed type random variables. One is continuous, the other is discrete. Okay, and so we would like to study these two cases. Okay, but so we first recall that a random variable x is called conditionally absolutely continuous given a discrete random variable n. Okay, so of course that x must be continuous. So x is a continuous random variable, and n is a discrete random variable. Okay. If for each n, okay, with the probability that capital N equal to n has positive probability, there exists a non-negative and integrable function on R denoted as F such that the conditional CDF which defined to be okay, so that this is actually okay. This is conditional CDF. Okay, and we know such that the conditional CDF of x given the event n equal to n can be expressed okay, as here so you can, I think, oh, okay, maybe I simplified it. Okay, for all x in R, okay, All right, so to verify whether a random variable x is conditionally absolute continuous given a discrete random variable n, we have to find a bunch of non-negative and integrable function, okay, for each n such that the probability of this event is positive, okay, right? So for each, which means that n is just a possible value, right, of n, and for each possible value n, that we should find such actually is a probability density function. Okay, so it is non-negative and the integrable function. So that the conditional CDF of x given the event that n equal to n can be expressed as an indefinite integral of this function. Okay. All right, and as discussed in section 6.5, okay, the random variable x, okay, is absolutely continuous with a PDF. So this PDF, it would be summation of O n such that positive okay. All right, so if we form the weighted sum of these density functions, okay, then we have proof, right, in section 6.5 that this function is a PDF of x, so x is absolutely continuous. Okay. Right, so we have done this in section 6.5. All right, so for convenience, we define that okay, for all n in R with probability that it is 0. Okay. Okay. So we know first that the x is absolutely continuous with this PDF. First, right? And then we can define the conditional. And so f of xn is called a conditional PDF of x given that n equal to n. Okay. Okay, so this is for all n in R. Okay, so that n can be any real numbers. Okay. And in this way, we can write that. So this is come to n. And p, okay, sum over O n. But this is after the convenient definition. Otherwise, the real definition of this PDF would be here. Okay? And so we will see. Okay. So this is the consequence of all this convenient definition. We have that. Oh, by the way, okay. All right. Okay, and if X and N are independent, the conditional CDF of X given that n equal to n becomes so that is and here in here we have okay. And because X and N are independent, so the joint event becomes to be, the joint probability becomes a product of individual probability okay, and you can cancel them. Okay, so this is actually the unconditional CDF. For all n in R. Okay. Then we have okay. So the conditional PDF of X given n equal to little n is the same as the unconditional PDF, okay, for this case. Now, the conditional expectation of x given that n equal to n is defined as okay. Provided that the integral exists okay, and if so, now if if this conditional expectation of x given y equal to y, all right, exists, and it's finite for all y in R, then we can define a real valued function on R as here the gy defined to be okay, then the function g of y is a discrete random variable again. Okay, and it's called a version of the conditional expectation of x given y. Okay, and also denoted as so we don't need to check whether G is Barré measurable or not, because for discrete random variable, any data parsing function is good enough, okay? As we proved in chapter 4 before. Hi. And for an omega in the sample space, okay, we have right, the value of this random variable at omega, which is, oh, sorry, and Okay, so it should be because we given a discrete random value, so n equal to little n here for all n in R. So Gn is here for all n in R, and G of capital N of n. Okay. Okay. And okay. Okay, so this is G of n omega, and it is expectation of x given n equal to n omega. Okay, and the expectation of this random variable x here so this is a summation of little n and g of n, and okay, and this here is the PMF of the discrete random variable capital N. Okay, so the expectation of the conditional expectation of random variable x given random variable n can be computed in this series sum. All right, and involving the PMF of discrete random variable n, and also the function g of n here, the function g of n. Okay. So now we will have a similar proposition. Seven point 5.1.AC to D. Okay. Now, so let x be conditionally absolutely continuous random variable given a discrete random variable n. Okay, so if x has a finite expectation, then the expectation of random variable x given that random variable n equal to little n exists, and it's finite for all n in R. Okay? And the expectation of n equal to G of n with Gn defined to be has a finite expectation with that its expectation is equal to the unconditional expectation. So again, X has a finite expectation. It's a sufficient condition for that, for this quantity exists as finite for all little n in R. Okay? So that this quantity exists is finite for all n in R, so that they can be used to define a function called G, right? Okay, and the G of n, as we know, this is a version of the conditional expectation of random variable x given discrete random variable n, right? So this random variable is a discrete random variable and also has a finite expectation with this, okay, identity, okay, right? So we have the result and the proof. All right, so because time limitation, so I was pre-C lecture notes. So I will send you lecture notes. Okay. Okay, so now in this case, X is conditionally absolutely continuous given discrete random variable n, and so we find the conditional expectation of X given n. But the other way, how about the other way? Okay, so as we discussed, so recall that for, as discussed in section 6.5, for a conditionally absolutely continuous random variable x given a discrete random variable n, the conditional probability of the event, or we just say the conditional probability mass function, the conditional probability mass function of n, okay, given that x equal to little x is defined as, okay, so we have defined to be if okay, so there are two cases. If the marginal PDF of x at little x is positive, then this is actually okay. So it's this one. For n. Okay, so this is the PMF. The conditional PMF is defined in this way. Okay. It can be seen. So we know if x and n are independent, we have that which is equal to O n in R. Okay? So we have this identity. So we have proved before, right? Has been erased already, right? Yeah, has been erased already, but we know that we have this identity, okay? And so you can cancel them, right? Well, oh, okay, thank you. Just here, yep. Okay, so if they are independent, we have this. Okay, and okay, so that, and then so the conditional PMF becomes true okay, and both case equal to unconditional PMF. Okay? So for all x, for all n in R, and for all x in R. Okay. All right. Now we define the conditional expectation of n given that x equal to detail x is defined as here. Defined the n and the n and use the conditional PMF. Okay. With that, okay, and this is, so if you do the computation, you will have n, and divided by, and this one, summation n, p and n, and which is the expectation of n itself. If positive, 0. Okay, so provided that the sum exists. Okay, the sum exists. Okay, now if this quantity exists and it's finite, so it is finite for almost all x in R. Okay, so we can define a real value function okay on R. So the gy is defined to be this quantity gx. Okay, if x in data and 0 if x not in data, where delta comp x equal is the x in R such that exists and it's finite. Okay? Right, so we can define this function. Okay. Now if G is Borel measurable, on R, then g of x, then the function of x is a random variable called a version of the conditional expectation of n given x, okay, and denoted as the conditional expectation of n given x. So we have and for any omega in the sample space, so we have that expectation of capital N given x. So for this random variable has value at omega, which is okay. So it's here, and this is expectation of N. Okay, if and 0, if okay, right, and the expectation of this random variable, okay, the expectation is here. So it's okay, so it's here. Okay, and okay. All right, provided that the integral exists. Okay, so now I state a proposition. Right, so let X be a conditionally absolute continuous random variable given a discrete random variable n. If n has a finite expectation, then expectation n, the condition expectation of random variable n given that random variable x equal to little x exists and it's finite for almost all x in R. Okay? So this is the requirement that this exists for almost all in R. And so this is 7.5.2. The function g of x defined in 7.5.2 x for real measurable on R, so that is a random variable. And okay, so now we can define a random variable, and which is called a version of the condition expectation of n given x. And this random variable has a finite expectation with the expectation is equal to the expectation of n again. Okay. And again, I will give you a lecture, the proof in a lecture notes. Let's see the lecture note. Okay. All right, so these four cases, they have a similar pattern. You see that we have similar results. We have similar results. The only requirement is that the central, the random variable under study has finite expectation, and the sign information can be arbitrary. Okay, in this case, the sign information x is conditionally absolute continuous given n, all right, in this case. Okay, so we show those cases. Okay, because we lay the foundation in chapter 6, right? In chapter 6, we consider conditional distribution there. Okay, and we use the results in chapter 6. We can have very specific propositions about the identity here. Because in textbook, it gives a very short statement, say that, oh, this is always true. Okay, it just gives you that this is true. But that the textbook does not give you any explanation. Yeah, I think the authors give a partial explanation for some cases. I forgot, maybe for discrete cases. Okay, but at least in the class lecture we elaborate for our cases here. Okay, and we have shown that this identity is true. Okay, all right. So in many practical, most practical situation, that these four cases will cover the cases you were studied in engineering disciplines. But next Tuesday, I will give you the most general results we have in probability theory without any proof. Okay, I will state the statement for you. Okay, so that you are able to apply this result in basically an arbitrary and the general cases. Okay, so yeah, and the idea, I think the idea behind conditional expectation of a random value given a non-random variable. The given random value is also we call the sign information. It is because that such identity gives us an indirect way to find expectations. Okay, so expectation seems, the computation of expectation seems very simple, right? But that is for some cases. In many practical situations, the expectation of random value is hard to evaluate. Okay, but with this one, with the two steps evaluation, the problem becomes to be solvable. Okay, and quite easy to solve. Okay, so this is alternative. Okay, and I hope that I have laid the foundation for you. Give you enough reasoning and enough explanation why this is true. Why this is true. The only requirement would be the random variable, all right? To be studied has a finite expectation. That is the only requirements for that. The other will be the companion requirement that. Okay, so the sign information can be chosen in a sense arbitrarily. Okay, so I'll stop here. Okay. Any question? Okay, before we leave this classroom. Okay, so I think this is the most sophisticated argument in